So we had this general estimator, and then a particular example is where you partition the space n at a time. And if you give me an x, I'm going to look at the cell in which the data point lies and the average. The data point. So this is a simple example. Another example is this k-nearest neighbors. Another example is where you have like a Gaussian kernel you put there. Another example is where you have like a box kernel. The box kernel is very similar to this, but not quite the same. So we're going to analyze this as a prototype, and it is hopefully going to give us a lot of intuition. So we're not going to analyze it in the context of classification, because as I mentioned, in classification, things are a little bit more subtle, because you only care about what happens at the decision boundary. So if you make a mistake, let's say, or like have errors for your regression function outside the classification boundary, you're not going to see it as much. And this was sort of evidence in this plot that the bandwidth that you choose, for example, this is for the Gaussian kernel. There is an optimal value that is actually this, for example, particular example. There's not much difference between like the best and like the worst. So there's like about like 0.05, like a 5% difference in its classification rate, like 6%. And so we talked about how to choose the bandwidth using either train test split or train validation test split and cross validation. What I want to do is like how to set it like analytically and analyze the problem. So if you like recall, this is the partition, that's the partition in space. And A of x is the cell of the partition that contains x. And so the partition estimator would be something like that. So I average the yi's over the x's that are in A of x, divided by how many of the xi's are in A of x. So this is basically averaging. Okay. And then we did go over some. So you switch to regression, the same estimator works in regression. In regression, things are simpler in a sense. So we often look at the mean squared error, and we talk about the optimal rule. The optimal on the mean squared error means just the conditional mean. So that's like the optimal rule. So the regression function is the optimal estimator, optimal decision rule. And then we went on to like this idea, like discussion of sort of meta risk or the statistician's risk, where you look at the risk of an estimator, but that would be a random quantity, and then you take the expectation under your training data at the end, and that would be the risk that you're going to analyze. So this is not the risk for a particular realization of the estimation procedure, or rather like a property of the estimation procedure across all the training data. So I'm not going to go over the details of this. But suffice it to say that once we look at this expectation, things would reduce to analyze something like that. So if I take the expectation of the training data of this, what we look at is this 0.5 loss function, and this reduces further to, and so this is the prediction error in a sense. The prediction, the 0.5 prediction error would reduce to a component which is a variance, conditional variance of y given x. And then the difference of the regression function to, so f of x is like candidate. This is your candidate regression estimator, eta of x is the true regression function. And so how much you're off squared error plus a term which is not really useful. So we need to go to this calculator. So this point wise lot to be introduced does that. And so the whole point was motivated looking at the difference of the function, the different function is good enough. So you can motivate it in a different way, but if you care about prediction error in the MSE sense, there is a part which you can improve. So set that aside. There's a part which you can improve. For example, I can take this f to the data of x if I move it, and this would be the best possible. But I don't know it, so that's the price that I'm going to pay. So in the end of at the end of the day, I argued that we're going to look at this quantity. So eta of x minus our f hat of x squared, and then we condition on the training x's. If you take another expectation under xn, that would be that pointwise beta loss one or beta risk. But in any case, we're going to focus on this part. Okay. So at the end of the story is that I just wanted to justify what we look at, and then I called f hat eta hat. So at the end of the day, we ended up with this quantity. Okay, so that's the thing that we want to look at. We want to look at the difference of the regression function, the true regression function minus our estimate of the regression function square, and then I take the expectation. This delta is expectation with respect to the randomness in y, the training y is conditioned on the training x. So I'm going to everywhere condition on the training x, but I implicitly also condition on the test x, because the x is small little x. So you're just carrying a particular x. But you're averaging over all the like y's. Okay, the noise of y given the x. You can forget about all of that. This is a quantity that we're analyzing. This is the easiest thing that you can analyze, and then it gives you intuition of what is going. So I have an estimator. That's going to be my, and you can see that the end area is like pointing out that this particular form depends on the entire training data, and also like the point that I'm estimating at. And so this is this eta x, this particular partitioning estimator that I'm going to look at. Okay, so what we want to do is basically, and then usually I drop at the end. So eta hat x is just this. Implicitly, you know that it depends on all the training. So it's random quantity. And then minus eta of x squared. And then I'll look at the expectation under the x. Sort of. Okay, so that's the plan. So I want to analyze this and show you where the bandwidth comes into play. Okay. Okay, so let's focus on this. So let me show you. Okay, so how should we go about doing this? Let me try. So plan for today is to analyze this quantity. Expectation of eta x, the true regression function minus our estimate squared. So where this a tilde is, if I apply to anything, it's just, let's say if I apply it to z, it's just z conditional on x1 up to xn, which I also write as x to the n. Okay, so all of the
with no tilde on the right hand side.
Right. So this is the usual regret. Yeah. Right. So my shorthand to math like right condition. So we want to analyze that. The first thing that we do, and then eta of x is that particular estimator, but there is something more general. So the first thing to note, I don't know what I should call this. But whatever this is, this has a decomposition. Okay. And this has this famous Bias-Nernst decomposition, which often occurs we also saw it when we like write down the prediction error, the MSE, relative to y, but the way to look at it is if you add and subtract the mean expectation of eta hat. So if I add and subtract the expectation, so this is the trick that you do for bias variance decomposition. I add and subtract the expectation of eta hat. Okay, so eta hat is random. It has expectation, which is non-random. Yeah, this entire thing squared. I'm gonna put a bracket here or like braces. Okay, so I just add and subtract the expectation of eta hat. And all my expectations are killed out, so you can ignore it if you want, but just to remind us that we're conditioning on the training. Okay, so that's the like algebra. And then you square the terms. So you square this. So the whole thing is squared, okay? So a plus b squared, right? You get a squared plus b squared plus between a minus b. So the first thing a is squared. So this would be like expectation of a squared plus b squared plus 2ab. So a squared comes out of the outer expectation. Why does it come out? Okay. Yeah, expectation is linear, so okay, so I can just do this. Expectation of a squared plus expectation of b squared plus twice expectation of ab. But I'm saying this is a squared. There's no need to take expectation because it's constant. Okay, so this expectation is constant, this is constant, but this comes out. There's this guy, expectation of b squared. So what is this quantity? That's the variance. So eta hat x minus its expectation squared, and then I have an expectation. So this quantity would be the variance of eta hat x. Now I don't put the tilde because they're all conditioned on training x's. And then I have this term, which again, a comes out because a is constant. So this is going to be twice a expectation of b. So it is the expectation of b. Zero. Why?
Expectation of eta of x.
But if you look at the expectation of this, so expectation of b by linearity, the first term comes out, which is expectation of eta hat x minus, and then I have the expectation of eta hat x. So the expectation moves inside, and so this would be zero. So this is constant. This quantity is constant. So it comes out of the expectation moves inside and applies to this, but that's the same thing as the first term, so you get zero. So this is zero, so the cross term goes away. So this entire thing goes away. So what I'm left with is a squared, which I'm not gonna plug in. So eta x minus expectation of eta hat x squared plus the variance of eta hat. Okay, so this is a fairly general formula. This is called the bias, or bias squared. So the quantity I'm trying to estimate is eta hat x, and this is my expectation of the estimator. So the expectation of an estimator minus the quantity of interest is the bias. Okay, what does the expectation does? Like what does the estimator does on average? Bias squared. What this is saying is that the MSE, this is a form of MSE, okay, particular. Or quadratic risk
the form of MSE is like has this decomposition bias squared plus variance.
Bias of the estimator plus the variance, bias squared plus the variance. Okay. And oftentimes there is conflict, so when you're trying to reduce the variance, usually bias goes up, by trying to reduce bias, the variance goes up, and so there is a
Balance. Any questions about this? Has anyone seen bias variance decompositions? How many people have seen bias variance? Okay, a couple of people.
So this is an example of it. Anytime you have MNC, like some error squared in the expectation, you can do this trick. And usually the constant goes away with this. So if you want to analyze that quantity of interest,
Which is this guy for us, it's a form of MSE. How close eta hat is to eta x?
I just have to worry about the variance. So how much eta hat x varies and how much it deviates from eta x. So
Squared. Okay, so this is fairly general, it works for any estimator at this point.
I'm gonna do, I wanna analyze it for the particular partition list. Does this sound good so far?
Okay, so let's keep this in mind. And then so let's now move on to the partitioning estimator.
So I want to rewrite the partitioning estimator in particular fashion. So I'm going to introduce this notation.
So remember we have training data. Rewrite. So this is general. Holds for a general estimator. Let's rewrite the partitioning estimator. So there we have a rewrite. So remember, so we had this training data x1, y1, dot xn, yn.
What I want to do is I'm going to look at
This object. Okay, so if you give me a set A,
we're going to count how many of the xi's are in A divided by the proportion of xi's that fall within A. This is called the empirical distribution of the xi's. Sometimes called the empirical measure.
if you know measure theory. Okay,
So this is a good approximation of the distribution of xi's. So what is the distribution? The distribution can write it as a generic.
for a generic x. So assume that we're assuming that x1 up to xn are IID from some distribution p. Oh, actually, this is not p. I'm going to write it as mu. This is the marginal distribution of x. And you can also assume that x is distributed like mu. And this mu is defined like this.
So the probability mu of A is the probability that x belongs to A. Okay. I'm not sure how you saw distributions in probability theory, like 100B or 100A. But this is the definition of distribution of random variable. So what is the distribution of random variable? It's a set function that tells you what is the probability that the random variable lies in that particular for any set. So if I give you this mu of A, which is the probability that belongs to A for any x, I have described the distribution of x for you. That's sort of the definition. It's not the PDF, it's not the TM, it's the definition of the distribution. Okay, so if it's continuous in the PDF,
For example, you would have a PDF for a continuous variable, there is a PDF, let's say P of X, such that I can describe this V of A, which is the probability, as integral over A of P of X dx.
But the new of A is the probability that X belongs to A is just the integral of P of X dx over A. But I can specify this without a PDF. And so that's what we're gonna work with. So that is the distribution of random variables, the set functions of the problem measure, that assigns to every set the probability that X belongs to that set. And this is an approximation of that. So this is the empirical version. So instead of the probability that the random variable belongs to A, if I have a training sample, this approximates that probability. You've seen this before, right? So hopefully, like, you remember all the things that we were doing is like based on this approximation. So this empirical distribution, or the new N of A, let's put an N here just to emphasize that this is an estimate. You can put a hat if you want on it to make it an estimate, like emphasize that it's an estimate. So this is a good approximation of the new A by a certain well-known fact. So why this is a good approximation? Certain law. So let me see if someone else knows. Why this new why sort of why new N of A is a good approximation of new A. Let this be the only thing that you learn in this class. You've been like saying this many times. But the first thing that it started with, like, so what is why? Why this is a good approximation when N gets large.
Is it the law of
Law of large numbers. So there's a law and there's something large. So large is N. Right? So, like law of large numbers, the sample size grows. This converges as N goes to infinity. This goes to that by the law of large numbers.
And we have independence that we need.
We have the IID, yeah, so you have to have the IID assumption, and we have it. Okay, by assumption, the xi are IID, so this is a good estimate. Converges as and goes to infinity to nu of A.
We are assuming IID. Yeah, that's key.
Okay, so the empirical distribution is a good approximation. And it works in a very general setting. You don't have to assume like this says density or like mass function works for any. Basically for anything for which this makes sense. And this makes sense for any random variable. So any random variable has this probability makes sense. So the reason why this is true is because this converges to the expectation of it's true. The expectation that indicated is a probability. So this converges to the expectation of the indicator, and the expectation of the indicator is the probability, and it's the same for all of them, right? Okay, so questions? So now, why I introduce this because you can now write down this partitioning estimator in this very nice form. If you remember, so what I'm going to do is, again, remind you, what we're going to do is that we're going to work with unidimensional, like one-dimensional x's. So, and then I'm going to assume that basically all the x's belong to, so x belongs to 0, 1. Like xi's, basically all of them belong to 0, 1. They're the same kind of, have the same distribution is, so they have maybe some PDF supported on 0, 1. So that's the P of X, the PDF of X. What I'm going to do is I'm going to support like divide this into pieces, okay, of length h. And so these are the cells of the partition. And here I have four cells. And then again, to remind you, I have this notation. If X is here, this is the cell that contains it. Okay, so A of X is always the cell of the partition that contains it. And so my partitioning estimator, if you recall, is going to sum over xi's in AX
yi divided by I from 1 to n xi in ax. Okay, so if you look at this, you recognize that if I can divide both the numerator and denominator by 1 over n, and you recognize that this quantity is, what is this? That's this nu n of a of x. So this is the empirical measure or empirical distribution of this a of x. Basically, this counts. It's like, or this fraction, proportion of the training data point that lies within the AX cell. Okay. And so if you like move that in, this is like goes inside the, so I just move it inside the summation in the numerator. What I would get is indicator xi divided by ax divided by nu n of ax. And I also put 1 over n inside. So I get 1 over n dot. This is like product. And then y. Okay. So now this is my weight. If you remember, I can write this as w of y. So my estimator is just summation I from 1 to n. So this is not new. We have seen that all of these can be written like that. So data dependent way, basically. This tells me how much the I sample I have to weight for this particular x when I'm averaging my i's. And this particular weight is 1 over n indicator xi in ax. Okay. So that's the nice format. Sounds good. Okay, so that's my eta of x, eta hat of x. Okay. And I know what, for example, this part converges to, which is good. Written it like that. Now, what I want to do now is to calculate the two quantities. So I need to calculate the bias and the squared and then the variance of eta hat. So let's now calculate bias, squared, and variance of eta hat x. Okay, so let's start with the bias. Or maybe let's start with the variance. Variance is easier. So variance. So eta, like, sorry, let's do variance. Yeah, variance of eta hat x, which is just the variance of summation I from 1 to n wix yi. Okay, so you can see now why my conditioning on the training x's is helpful. Because if you notice this, these weights only depend on the training x's. And the still that I have from the side, are conditioning on the training x's. So these weights are constant. Okay, so wi's are constant, but yi is random still because conditional on the training x is very random. This is yi. So what can I do with it? The sum of yi's. And then calculate the variance. The weight is constant. Right? Constant. It's what you have the sum first. And then move past the sum. If they're independent, are they independent? So what we're working with is like yi's conditional on x1 up to xn, because we're conditioning y1 to yn conditional on that. So given all the x's, are the y independent? If you think about it, it is because the pairs are independent. So x1, y1 is independent of x2, y2. So then a condition on the x's, still y1 and y2 are independent because y1 just depends on its own x1, not any other, anything else. So even conditionally, they're independent. So they are. So yi's are independent even when we condition on xn, which is this. So I can move it past. So let's do this as a side note here. That should small side note goes there. So this is going to be summation I from 1 to n variance. If they weren't independent, then you would get the covariances as well. But fortunately for us, so sums out, comes out, variance goes in. And then the way i's are constant. Now I can pull them out. So what happens when I pull them out? Yeah, they come out the squared because it's a variance, so I get the squared. And then the variance of yi. Okay, so this is really the variance of yi conditional on all the training x's. So I don't remember if I told you about this, but we talked about this, or so what is this going to be? So this is really variance of yi conditional on x1 up to xn. It's not hard, again, to convince yourself this is really variance of yi given xi. Because given xi, y dependent on everything else, and this is really the conditional variance of the distribution. So, so remember there is a distribution, we assume, generally. And all these conditional variances are related to. So this distribution has a marginal for x. So the one way of describing it is the marginal of x, and then sort of times the conditional of y given x. Okay, so you can decompose it into like the sense product of these two things, and the conditional of y given x is what we're dealing with. And this has a variance, this particular distribution has a variance, and that's that variance. Okay. So there is a variance associated with this. I can say variance of y given x is equal to x, for example. And this potentially could depend on x. But here we're going to assume that this is really constant for simplicity. So this is really would be like this conditional variance xi if you want. It potentially depends on xi. But I'm gonna assume that it's really constant. If you go back on the notes, we also assume this. So we assume the conditional variance of y given xi is constant for simplicity. Or simplicity. So this happens, for example, if you have a regression problem, which has a mean plus some noise, which is just has the same variance. Sometimes it's called almost stochastic, as opposed to typical stochastic. Not pronouncing it. So the variance doesn't determine everything. Okay, so then things would simplify. What can I do here? All of that. Cut. And then create another note here. So this is the side note here. We assume for simplicity that variance of y given x does not depend on x. Okay, so if that's the case, then my formula for the variance, so basically variance of a dot x becomes sigma squared comes out because all of them are the same, summation I from 1 to n wix squared. Okay, almost done. Sounds good. And then one more thing is that's wi squared. Oh, sorry, that's wi. When I square it, what we have. So we square this. Copy. So that's wi. So what will happen if I square this?
Whenever x is then kx, there's 1 by n squared, n squared.
Right, so this is like gonna be sigma squared and then summation I from 1 to n. 1 over n squared. The indicator squared is just itself because it's either 1 or 0. And then nu n ax squared. And then something very interesting happens here. So I'm going to pull one of the 1 over n's out. So you get sigma squared over n. And then the denominator does not depend on I, so this also comes out. So summation goes on the numerator divided by nu n of ax squared. And we notice that this thing is the copy of that empirical thing. Right, so sigma squared n nu n of ax divided by the squared, and so one of them cancels out. So the variance is really sigma squared over n times nu n ax, which is a pretty nice statement. Okay. Right. Sounds good. This used to be an exercise. Still can assign it as an exercise if you go through it for yourself and convince yourself. There's nothing very difficult here. It's just some calculation. But this form is very interesting. Question. Why it's interesting? Because if you remember, this nu n of ax converges, or for any a, it converges to the nu of a, which is the probability that I assign to a. So assume, let's say I'm going to assume that, let's say the marginal distribution of xi's are uniform, let's say, for simplicity. Okay, so by the law of large numbers, I'm going to say this is approximately, because there's n in it. If I let n go to infinity, this is going to go to 0 because n goes to 0. But I mean, you can make this more precise, but approximately for very large n, this is really nu of ax. Okay, because for very large n, this converges to nu of ax. And I want to say what nu of ax is, so by the law of large numbers for large n. We can make it precise if you like, if you know the all field.
notation, like converted probably, but this is good enough for us.
So I'm gonna say that that's the case. Okay,
So for very large and this new n is convergent to mu of x, so I'm just gonna place it there. So that's my variance for very large n. As you can see, it's going down like sigma squared over n, and there's a factor here. Yes,
So like intuitively, the nu of AX is like a measure of size, right? So
yes,
as the AX regions get larger, this
Gets bigger.
variance of eta hat, our estimator,
goes down.
goes down.
Yes, so I want to show you what exactly it is. So exactly, so it depends on this measure depends on the distribution of x, but let's say I'm on 0, 1, and the distribution is uniform. So it has a density which is 1 and then drops to 0. Okay, and if you subdivide this into, let's say, 3 pieces or 4 pieces, let's say 3 pieces. I have a partition of, let's say, 3 cells, and each has side length h. Then it doesn't matter which one AX is. So if AX, for example, is this one, so what is nu of AX? Right? If I have this, this is like the probability that the random variable lines into AX.
1/3.
1/3, right? So okay, that's it in terms of h. Let's say I divide this into in this particular case it's 1/3, but I want to do it in terms of the general h. So I partition it into a number of cells, each of length h. The number would be 1 over h. So I have like roughly 1 over h cells, each of length h. So what is the probability or the chance that a random x is
H.
h? Yes, so it's uniform, so it's like h divided by 1, basically. So this is going to be in general h, no matter which of the cell partition. So in the end, the variance, that's the punchline is the variance of eta hat x is approximately for large n sigma squared over n divided by h. Yes, you can see the bandwidth here. So the larger it is, the smaller the variance. So you're averaging over more things, it goes down like 1 over h. If h goes to 0, then it just blows up. Okay. The variance is better. I let h be bigger. I'm going to aggregate over more, and this is sort of, you can easily see. This is a better, so this is going to be going down because eventually this is going to. Oh, and the best is like negative 0, 1, average for everything 1. So variance goes up if h goes down, vice versa, decreasing in the bandwidth. And like equivalent to bandwidth. Here it's like basically the partition like the next side. Okay, so we analyze the variance. That's it.
When you use law of flat numbers, what happens to sigma square by n?
What did you say?
There is a sigma square by n, right?
So I have the sigma squared over n here.
Will that not go to 0?
Right, so that's why I'm saying approximation. So this is the order of this. So this is going to be of the order of this. Eventually, it's going to go to 0, right? So you want to be precise. If you want to be precise, it's something like that. So nu n a of x is really nu of x times 1 plus OP of 1. So it's like this plus something which is like going to 0 in probability. OP of 1 equals 0 probability. Then 1 over 1 plus OP of 1 is still 1 plus OP of 1. So in the end, you can say that this quantity is sigma squared NH. The first order is 1, and then the rest, like, and the first order is of this order. And then there's something that So if I divide this by this quantity, it's gonna go to one. But as a whole, it's gonna still go to zero. But this is saying the first order. Uh, this quantity is this. So the best way to think of it is that divide this by that equals to one. So, okay. Sounds good. So what remains is the bias. No questions, comments. So this wasn't that bad. Right? No. It's just simple properties. So the bias is a little more tricky, but not too much. So again, my estimator is something like that. What I need to do to calculate the bias, I have to calculate the expectation. Okay, so let's try to do that. So bias. So we need to calculate the expectation. Expectation tilde of theta hat. And this is expectation of summation I from 1 to n wix yi. Okay. So what kind of simplification happens here? Yes. So it's similar, the weights are, and then expectation, this is always true because expectation is linear, so this goes in. Here, I don't care about independence. And then wi's come out because they're also constant. So I get this times yi. And this is really, again, under the hood. It's like expectation of yi given the rest. And again, by conditional independence, it only depends on like expectation of yi given xi. Now this is the moment what is the expectation of yi given xi? Eta of x. Great. This is the eta of x. Expectation of like a generic y given x is equal to little x is eta of x. So now what is this? It's very close, but there's no x here. There's xi. So this is going to be eta of xi, because this is saying once I condition on an x, expectation of y given that particular x is just eta of x. Or you can say expectation of y given x is eta of x, that's like random x. Expectation of y given xi, they have this all the same as their usual, so the same conditional mean. So it's like a single function, but the value of it xi. So we end up with something like that. X and then eta of xi. Okay, so we're basically like averaging the true function. So you're averaging eta at xi's that have high weights. Okay, so you really want eta of x, level x, but you're not going to get eta of level x, you're going to get average of eta of xi's that are nearby. And that produces the bias. Because you're not evaluating that particular prime, you're just evaluating over everything, you're averaging over everything. And xi that you see in the training, you're not going to see this particular x value in the training. You're going to see xi's, you're going to average over these x's. The closer they are to x, the better. Okay. Well, good. If the bias conditional, it's a linear conditional, so it's okay. But its quantity is
only thing I'm turning excess, and that's what we want. So far, so good. So I want to do a little bit more. So we have these weights, right? And I can plug this into that quantity. And so if I plug that into this quantity, I would get, so I'm going to put that nu n ax out. So there's a nu n ax that I pull out, doesn't depend on I. And then I get 1 over n summation I from 1 to n indicator xi in ax and then eta of xi. So this formula, by the way, works for any of these local averaging. So when the local averaging looks like this, so this formula up to this point works for any of them. The same goes for the variance. The way that we wrote the variance, and this is for a general local averaging. So this works for the k-nearest neighbors, for the kernel estimators. So this comes out up to this point, works for all of them. And once we plug in the particular form of the way for the partition, that's not specific to the partition, but these formulas still apply. So for example, this helps you find the conditional variance of the nearest neighbor. Very simple. So that's after we plug in the weight for the, so works for any local averaging estimator, like particular. So this is for the particular. Okay. So I know asymptotically, as n goes to infinity, what happens to it. So that we're going to converge to this edge in this particular case. So what happens to this other term? So this other term comes out, the whole thing comes out that when I plug in. Okay, I plug in the weights, and you can verify that this is what happens. So what about this? So what can we say about this quantity? As n goes to infinity, does this converge to anything? What happens to this as n goes to infinity? It's 1 over n summation of a bunch of things. But each term depends on xi. So this whole thing is a function of xi. Like, let's say it's like zi. Does that look familiar? 1 over n I from 1 to n zi, and zi's are IAD. They're independent and they have the same distribution because xi. So this is just a function of xi's are IAD. So this is really like some function of, let's say, g of xi, but xi's are IAD, so g of xi's are IAD as well. Or expectation of one of them. Okay. Or two of it. Yeah, so okay, so let's do that rate. So it's going to converge to, why does it converge to? Law of large numbers. Okay. Law of large numbers, n goes to, you can see this like how useful it is. So it goes to expectation of, let's say, z1, or if you want, expectation of g of x1, one of them. which is equal to what? Oh, I think I lost there. So suppose the x's have density Tx. In this case, it's uniform with this two general. So if xi for x1 has density Tx, what is this one? And you write the expectation of g of xi as terms of the density of x. Integral, yes. So can you tell me how to write down the integral?
Well, G, thanks.
Right. I don't know what happens. Okay, integral of right, g of x.
Yes, fx. But no, it was knee. What was it?
It was, yeah, okay, you're good, so yeah, so I used to write it like that. Or like d mu, say, d mu of x, but that's measure theory, so that's like fancy. It's just, let's say this, dx, dx. And this is good, that's the same mu. And distribution, so if you work with distribution to write d mu of x, like the derivative of the distribution, but you understand this means with no measure theory.
Is the integral over A?
At this point, no, but it comes out. So this is like g of x, just the entire thing. Right? If I have, I wrote the entire thing as g of xi. So this is going to converge to the expectation of g of one of them. One. So it's like integral of gx, dx, dx. So I can plug in gx, it would be indicator of. Now this is going to be like problematic because I have an x here, which I don't want to confuse with. So let's say t, for example. This is like a dummy variable. I think I do u in the notes. So integral, I mean, it's just the variable integral, doesn't matter. So u in a of x, because I don't want to confuse. So eta of u, tu, du. Let's do properly somewhere else. So expectation, this comes here. Integral of g u p u, u, that's the density of x1 or x. All right, so this is going to be integral gu is just indicator. Where you have xi's, that's going to be u. U in ax, tu, du. Okay, now I have the indicator. So this is going to be 0.
There's an eta.
Sorry.
There is one more.
Yes, eta, sorry. There's eta as well. Thank you. Eta u, pu, du. So this indicator is going to be 0 or 1. And it's only 1 when u is in ax, so I can really write it like this. And then ignore that. So eta u, pu, du. Or if you like measure theory, it's a little bit cleaner to write it as measure theory. So you don't have to know what it is, you can pretend to know. So it's like integral ax, eta of u, d nu, the same nu that we talked about, right? Nu of a was like probability of x in a. Somehow if I can differentiate this distribution, that would be, it's like this replaces that whole thing. Okay, so I'm just averaging eta x, so this is like an average, weighted average. So eta with the weights that are these densities over the atoms, over the entire region. Okay. So what it does, let's say in the case, so okay, let's is this sort of clear? So by the law of large number, this converges to that, and then I had a term here. This one by the law of large numbers converges to nu of AX. Okay, so if you plug everything back together, the bias, so expectation of eta hat x, so it converges to as n goes to infinity to 1 over nu of x, AX, and then this quantity, AX, eta of u, I'm going to write it d nu of x, or du, or yeah, it's going to be a little confusing. In any case, it's just
The same quantity that appears here, so this quantity is if I integrate one here. If I integrate d nu, the density over AX, I get this. Now I'm integrating eta u.
So what this really is like a weighted average.
Okay, so the sum of the entire weight is this. So 1 over this, and then I integrate this one.
So in the simple case that we have, simple uniform on 0, 1, right? 0, 1, this is 1. So that's that distribution. This I can just write as 1 over, this turns out to be h, right? So AX has length h, remember? An integral over AX, again, the same thing. Eta u, and then this is just 1, that's a du.
The density is 1. So I'm basically averaging, you can think of it as sort of,
it's some sort of interval like this. Okay, so what happens, what I'm saying is if you have the function, your regression function is something like that, what this is going to do is going to take the integral of this, averages this out, right? This integral is going to average it over this region, and then divide by the length. So you get some sort of an average function here. Let's maybe expand it a little bit better. So if you wait it. Let me show you the bigger picture. So it's like 0 to 1. So let's say I have something like that. And let's say my h happens to be like this big. It's not too bad. So if this is very variable, so let's say something like that. Okay, and then h is something like this. So this is AX. The length is h. What I'm going to do, I'm going to integrate this out and divide by h, and I'm going to just get some average. So over this region, it's going to be just constant. Over this other region, it's going to be another constant. It's like the average value of the function. So this is going to be average value of this. Here is going to be that. So what I'm really doing, this estimator is like averaging,
like approximating this regression function by its average.
and if you think about this, like partitioning is exactly doing that. So over these regions, our estimator even is constant, okay, because this average is
Over this region, it's going to be constant. The same, all the points x that are here are going to have the same eta hat x, and it's going to be the average. So there is some variance. So in practice, what you have is this is not the actual thing that you observe. The actual thing is like a level which is variable that has a variance and a mean. So it's going to be centered around this, but it's going to also go up and down. So the up and down is by the variance. What you're computing here is the mean. So the mean is going to be this constant, piecewise constant function. Okay.
So it's nearly a piecewise constant. So eta, the bias is like approximately 1 over h eta x is a piecewise constant.
Right, depends on x because x here, and it's easy to convince yourself that it's really averaging the function. Okay. Integrate this out and then divide by 1 over h, which is the size. And so it gets better if you decrease h. So if I decrease h, I'm going to average over smaller pieces. Okay, so this is maybe the one that whose partitions. So the bandwidth is like this, right?
So it's gonna be like piecewise constant, but you can see it's a better approximation. If I average it over smaller edge. So this is in general not gonna, so what we want is we want this to be, we want to compare this for the bias, need to compare this. Compare it to eta of x. So eta of x is really, for a given x, eta of x is like here, the difference to this constant line is the bias. So for example, here at the end, I'm doing a very good job, but here I'm doing bad. So given an x, how far the actual thing is from this expectation is my bias. So bias is gonna be, that's the absolute value of the bias is eta x, the true thing, minus 1 over h. And this is non-zero, okay? For any fixed edge, this is gonna be non-zero. So the only way that I can make this zero is to let h go to zero. As h goes to zero, this thing converges as h goes to zero to eta of x. So the average of the function over that interval converges to eta of x. Sorry, so this is going to only go to zero only if h goes to zero in general.
What is that green curve?
That's the
Curve
eta.
of eta.
This is the eta, the actual eta of x.
Do we know that?
No, we don't know it, but we want to approximate it. And the bias is like how far you're from the. So eta, we're computing eta x minus eta hat x, expectation squared. And then we have is the bias variance to composition. So we're looking at what are we looking at? You're looking at this quantity. Yeah, we're looking at this quantity. We compare it to the true eta x. And then this is the bias. And it turns out that the expectation here involves this eta x, but not the eta of x, but the average of eta over that some interval. Right, so the expectation that this contains the true function that you don't know, which is good, but not the actual value of the function of the point, which is average. So that's reasonable. And so you can very much easily see that I need to let h go to zero. For this to go to zero. And if I let h to go to zero, then what would happen is I blow up the variance. So the variance was, but like, so I need h to be large, but the variance to go down. But if h is large, my bias is large. If I want to make the bias go to zero, I have to let h go to zero when this goes up. So I have to balance out, given a particular thing, there's an optimal value of h. So one question is, can I do better? Can I give you like some approximation of the bias? So can I sort of give you an approximation bias that shows you how fast it goes to zero as a function of h? Answer is that you have to make some assumptions about eta. Okay, for the variance, you didn't need that. But here, for example, if eta itself is piecewise constant, you'd imagine that you get a much smaller bias versus if something which is like a sine wave. If you have a sine which is varying very much, approximating by something which is piecewise constant is going to be much harder. So I'm going to have to make some assumptions. So the smoother edge is, or the at least like something closer to this piecewise constant or smooth. If it's smooth, it's not bad. So it's like suppose that this is like that. Like this is the regression function, then like piecewise constant approximations are not bad. But if it's like this, piecewise constant approximations is bad. So that how fast it goes to zero, this error, depends on the nature of the smoothness of it. So next time we come back and just make one simple assumption.
and tell me what the order is. And then we can write down bias variance decomposition, what value H optimizing. Okay, but I'm gonna post this, you guys can go over this and think about it. This is just, it captures the essence of a lot of these ideas in so this is the machine learning about bias variance decomposition. Okay. Sounds good? Questions?